So we go about approaching this.
Yes, sir. With the given information, sir, we can find the cost per hour, sir, or the power, the MW cost per hour, sir, for each for lambda 1, 2, and 3, sir.
MW cost per hour, I don't know what that, I don't understand what that means. You mean the cost per megawatt hour?
Yes, sir.
So you want to find, oops. You want
But
to find,
first you have to differentiate the expressions that we got, sir.
cost per megawatt hour. All right. So for lambda 1, just give me what you have. Lambda 1?
So I have 2 times 0
No, just give me the
0.07.
final. Just give me the final.
Oh, 17.4.
Lambda 1?
17.4.
17.4.
Lambda 2, 19.
No. I don't want value. I'm saying that I want the final expression.
Oh, I was just saying it a while ago, sir.
Oh, you were telling me 2 times something. So I'm saying just give me the expression having multiplied it. So it'd be 0.1.
Okay, so 0.14 times 60 MW.
Times P.
Right,
Plus
yes,
what?
sir, times P plus 9.
Lambda 2?
So 0.11 times P2 plus 6.
Lambda 3?
0.09 times P3 plus 8.
Okay. All right. Thank you, sir. Mr. Allen?
All right, sir.
Allen? Mr. Allen?
Yes, sir. Yes, sir.
Next. What next we do?
Find the value of lambda 1, lambda 2, and lambda 3
At what point?
at the minimum MW. Megawatt, sorry.
At minimums, lambda 1 is equal to?
$17.4 per megawatt hour. Lambda 2 is 19.2 dollars per megawatt hour. Lambda 3 is 16.1 dollars per megawatt hour.
All right, so now that I have these lambdas, next step?
You're going to find the most efficient cost, which is unit 3.
I go from there.
Sir, you have 2 lambda 2 right here, sir.
That's not critical. So, where do I go from there, Mr. Allen?
The lowest value is the most efficient,
Okay.
which is the value for unit 3.
And so what do I do with that?
So in order to the second step is to test the second most efficient cost, which is 17.4.
Okay, so so how do I test that?
Test it with lambda 3 values, which is 17.4 equal to A3.
Okay, which is, so 17.4, give me the expression now, equal?
A3 P3 plus B3.
Oh, let's give me the expression. Let's give me, what must I be writing? Give me the number, give me what I must be writing.
Oh, the number, oh, sorry. 0.09. 90. Oh,
P3
P3 plus 8.
plus 8. All right, and P3 from this is equal to?
90.
Okay, 90?
Yes, sir.
All right, so that's 90 megawatts.
100
All right. So what's the implication of that?
Is to find out if
You have found 90. So what does this 90 tell you?
90 is the minimum power. The minimum power that the unit 3 offers.
Let's look back at the question. Yeah, but that 90 is what we use to calculate this. Isn't that so?
Yes, sir. We are running a test to see if the second most efficient will surpass its maximum.
Well, it's not about its maximum. Well, all right, go on. So what is P3 equal to from this expression?
104.4.
104.
Allen. I'm speaking to Chavez Allen.
104.44.
104.44 megawatt.
Yes,
All
sir.
right. All right, cool. So what does this tell you now?
This P3 did not pass its maximum power. This means that all power will be taken from all 3 units.
All right, so is it a matter of it not passing its maximum? Is that really what you're testing?
Its efficiency. We are testing its efficiency.
Yeah. Okay. Ms. Barrett? Shaki? Thank you, Ms. Allen. Ms. Barrett, what are you really testing?
Sir, my background is a bit noisy, sir.
Yeah, man, me I go shout. You want me shout? Can you hear me now that I'm
I'm
shouting?
hearing you.
Huh?
Yes, sir.
All right, so I'm asking, what is he really testing?
Sir, you're breaking up.
What is he really testing? By putting in this, by using that expression, what is it that is really being tested?
Sir, the highest efficiency, sir.
How would you know it's the highest efficiency?
Sir, I don't hear you a while ago, sir.
How would you know whether or not it's the highest efficiency? What is it that would have told you that it's the highest efficiency, since you are saying it is the efficiency that we are testing? What answer would be saying to you, yeah, man, it's the highest efficiency?
Sir, I'm changing to the minimum cost, sir. Minimum MW.
No, that's not what I'm looking for. Mr. Blake?
Sir?
All right. That's not what I'm looking for, Ms. Barr. I'm gonna move on. Mr. Blake, Roger?
Yes, sir.
So what exactly are we testing? Why is it that we went ahead and did that?
So the initial test, since we know that the highest highest operating efficiency one is unit 3. So the initial test carried out on unit 1 is next to the most efficient unit, so equal to the 17.4.
So by testing it, what are we really looking for?
The one that is second to the most efficient.
Yeah, man, I understand that, and you said that before, and I agreed with you. So I'm now asking, by making the test, what exactly are we testing for? Why is it that we are testing it?
To how much the units consume in terms of the cost, the incremental cost, fuel cost.
Okay. All right. Not exactly. What we are doing, ladies and gentlemen, in making this test, you're seeing the point at which another unit, in this case, unit 1, will be required to also produce output. That's what you're really doing. Because you have already established that this is the most efficient. I think everybody correctly said that. Agreed? When you look at the next unit in terms of efficiency, you are now testing to see what additional output would have come from unit 3 before unit 1 would be required to also produce additional output. So it would all depend, yes, because for example, Mr. Allen was saying, because it didn't reach its maximum. That's not the critical thing, because it all depends on the total that you are supplying to the network. So if the amount that you are supplying to the network to meet the total demand is such that all the additional power could have been supplied by unit 3 without having to go to units 1 or 2, then you would do that. Do I make myself clear?
Clear, sir.
Because in this particular problem, you know that the total is 800. Yeah? And I suppose by virtue of what you have already done, in terms of the exercise, you know that, unit 3 had reached its maximum. And so, that's where the maximum discussion is coming in. However, based on what I have here, we have just added what? An additional 14 megawatts onto unit 3. Let us add these up. That's 180, that's 270. Right? I could have given you a question and said, what is the share when supplying 280 megawatts? All right. Now, in supplying 280 megawatts, when you do this test, you would have seen that unit 3 would put out 104 before unit 1 starts to provide output. Yes? And so what that would say to us is that the mix is that P1 would be 60, P2 120, yeah, and P3 would be 100 in order to meet 280. I hope this is clear, right? You're not testing about maximum. You're looking at whether or not you would be able to meet the total demand by virtue of the additional output you would get from unit 3 in this case, in this example. Yes? Is that clear? Have I confused anybody?
Yes, sir.
Yes, sir. Me too quite serious, yes, sir.
Pardon me?
So I don't quite get what was being said.
All right. I'm trying to explain the reason we conduct this particular test. And I'm going back to what Mr. Allen said. Mr. Allen said it was to test whether or not unit 3 would have reached its maximum. And I am correcting him by saying you're not testing to see whether or not unit 3 reaches its maximum. You are testing to see at what point in terms of output of unit 3, unit 1 would also need to come into the picture. Based on what we have done here, it means that unit 3 would have only added 14.44 megawatts to its minimum output before unit 1 would also be required to be putting out additional.
Sir, excuse me. Last week you said that the test was to show how much power unit 3 would produce before it become as if inefficient as unit 1. Is this the same thing you're saying?
That's the same thing I just said.
Okay, sir.
So because unit 3 had a minimum of 90, yes, that's the minimum. It reaches 104.44. And when it gets to that point, it is now as inefficient as unit 1. So it means that both unit 3 and unit 1 will now be putting out additional power to the system. That's why I just said, if I had asked you to determine the breakdown when supplying a plant demand of 280 megawatts, then the breakdown would have been unit 1 would maintain its minimum of 60. Unit 2 would maintain its minimum of 120. But unit 3 would have increased its output by 10 megawatts to give you 100. You add up these, you get 280. This question that I have given you asks you about meeting a demand of 800 megawatts. So obviously, having done this test, yes, having done that test, you would recognize that the units, unit 2 and unit 1, would have to be in the mix in order to meet the 800 megawatts. All right, now, where was I on the list? Mr. Bruce. Mr. Bruce? Mr. Bruce? Not a good sign, Mr. Bruce. Mr. Burns?
Yes, sir.
Know that we recognize that the additional units, the other units, will have to be supplying power. What's the next step?
We would have to find AT and BT in order to find.
AT is equal to?
1 over 0.14.
Okay, go ahead.
Plus 1 over 0.11 plus 1 over
Go ahead.
0.09 inverted.
And that gives you?
0.0365699.
Thank you, Mr. Burns. All right, and BT?
Be equal to AT times 9 over 0.14 plus 6 over 0.11 plus 8 over 0.09.
Okay, and that gives you?
7.596.
Okay. All right. So Campbell?
Yes, sir.
All right, so give me the equation for lambda.
All right. So that would be the 0.0365699. multiply by the 800 megawatts that will be supplied by the system, plus the new BT, which would be 0.596.
What does that give you?
All right, so all right, my values are slightly different because I did some rounding, but my final answer for the new lambda is
Some
30
rounding for what?
for when I'm solving for lambda. I rounded up the alpha t and the beta t to 0.0366 and 0.7.60.
You use 0.0366.
Yes.
All right, so you know I'm going to deduct marks for that because I think I have warned everybody enough that they should try and use as many decimal places as possible for AT. I'm almost sure I did that. So even if you write down something different, I expect you to use the calculator value. So I'm not going to take your difference. So Mr. Copley, thank you, Mr. Campbell. Mr. Copley?
Yes, sir.
Lambda. What value you get for lambda?
My lambda was,
I am assuming you didn't round off also.
no, sir.
What?
My lambda was 36.8422.
36.84. Remember, it's dollars and cents, okay?
Yes, sir.
All right. Okay. So based on what? Based on that lambda, we are substituting that into the formulas for lambda 1, 2, and 3. Is that the case,
Yes,
Mr. Kaplan?
Yes, sir.
All right, so what did you get for P1?
P1 is 198.872.
98.872. P2?
280.3836.
80.
Yes, sir.
Point
3836.
P3?
320.4688.
320.4. Go again.
4688.
All right, cool. But Mr. Copley, we don't have a problem, man. Eh?
Yes, sir.
So we're going to solve a problem. By the way, what's the problem here?
Because P3 maximum output is 300. Repeat that, sir?
Or we're going to solve it. We have identified the problem, so we solve it.
We need to allocate to another plant.
Another plant.
I can't hear you. You're breaking up.
Yeah, what do you mean by another plant? When you say another plant?
The additional load that's higher than the
Yeah,
300.
but what I'm asking, when you say another plant, is there an issue with you saying that? Well, I have an issue with you saying it. I want you to find the issue and correct it.
Another unit, sir.
Okay, another unit. That sounds a little better. All right, so you're going to assign P3 as 300 because that's its maximum. You're constrained by that. All right, so having done that, what's the next move?
We're going to sub P3 for 300 megawatts into the formula.
Go again?
Sub P3 for 300 megawatts into the formula.
Which formula?
The lambda, sir.
Oh, you won't be able to do that. What you know is that the total, All right. No, that's not the approach. That's not the approach. So let us, I'm gonna go down the line. All right. Thanks, Mr. Captain. Next.
Okay, sir.
Hold on, this thing changed. Just a minute. Okay. So, Mr. Crasdale.
Yes, sir.
Now that we have this issue with Unit 3, how do we solve it?
Sir, would you find a new AT and BT?
We reach this one, sir.
Sir, because the leftover will be 500 megawatts, sir.
We reach leftover yet? You're not telling me nothing about that yet. How we reach leftover?
Sir, what's the question, sir?
We have just recognized that we have a problem with Unit 3. So I'm asking, how do we proceed?
Sir, you need additional power supplied by the other units.
All right, go on. I'm listening.
Oh, yes, sir. So, for what I did, I used AT, a new AT using the other two units, so 1 over 0.14 plus 1 over 0.11.
What I'm trying to get at, I want you to be systematic. You know you have a problem with Unit 3. The problem is that based on the lambda calculated, it is showing that Unit 3 would have exceeded its maximum. So we set Unit 3 to its maximum, which is 300. Hence, 500 megawatts, which is equal to PT minus P3, will be supplied by units 1 and 2. We have to be complete, eh? So now that I know that, yes, we are now dividing 500 megawatts between units 1 and 2. So you're telling me about your new AT. So AT is equal to?
1 over 0.14 plus 1 over 0.11. And the result of that inverted to the minus 1. So 0.0616.
Yeah, one of the round offers too.
So actually, that's what I got in the calculator, sir. I got 0.6160000.
0.616.
Yes, sir.
Wow, brilliant. Okay. And so BT?
0.06.
Yes, sir. 0.0616, sir. BT is.
Hold on, just a minute. 0.0616.
0616.
0616. Okay. 0.14.11. Okay. All right. Cool. And BT? Let's give me the final value.
7.32.
All right. So lambda is equal to
0.0616 times 500.
That gives us
38.12.
Now, I want you to take note of something. Please note that when you contemplated Unit 3 being a part of the supply, yes? I want you to note the cost was $36.84. So what that is telling you is that because you included that efficient unit, the cost was lower than when we are just using the other two, which are less efficient. So you see the cost going up. All right, I just wanted to make a note of that. So we now know we have 3812. Thank you, Mr. Carsdale. So Daly?
Yes, sir.
So from this, what you get for P1?
For repeat that, sir.
What did you get for P1?
P1 is equal to 208 megawatts. And for P2, the value is
exactly 208?
Yes, sir.
Yes, sir.
And P2?
Is 292 megawatts.
92 megawatts. All right. So we now have P1, 208, P2, 292, and P3, for unit 3, we have 300. All right. And if we quickly add those, then we get our 800 megawatts. Is there anybody who does not understand what has been done?
Excuse me, sir. Hello?
I'm listening, man. Go ahead.
Oh, yes, sir. It's not really to say not understand. I understand everything that has happened, but I was just trying to make a better clarification to say at the initial start, why did we assume that the entire units, all units are contributing to the load, and find that first AT and BT, including all three units at first. What I'm really asking, was there another way to find out from the beginning that we would have maxed out the unit 3?
Technically speaking, that would, you would not be able to determine that from any of the data that would be available. It would really be an intellectual guess at best. So you'll be guessing that you would have reached the maximum, but there's no way to just look at the information that you were given and make that determination.
Okay, sir. So hence the necessary tests and checks has to be done to ensure that, because we could have found out that one of the other units were probably could have been maxed or reaches its maximum before.
All right. Let me tell you why I would strongly suggest that you would not go any other route. This question would have been turned on its head if I had asked you to determine the breakdown for 750 megawatts. Can you see that?
It would break down, sir?
Saying the question would have had a completely different look if I had asked you for the breakdown in terms of supply from the different units.
Yes,
meeting a demand of 750 megawatts.
Yes, sir, because as you said, the load is, it's supplied differently.
So let's do, all right, all right, we still have 9 minutes. Just to expand a little on the question that you have asked. This first AT and BT that you calculated, just quickly put in 750 megawatts and calculate lambda for me.
Sir, 35.02344.
All right. substitute that in lambda 3 for me and tell me what value you get for P3.
So 300.26.
Huh?
300.26.
300.26?
Yes, sir.
All right. Well, I was, guessing in terms of the 750, but I could have said 740. The point I'm trying to make, however, is that if I had given you a slightly less total demand, yes, than the 800, you would have absolutely no way of determining whether or not unit 3 would have reached its maximum by just looking at the values. That's the real point I'm trying to make.
Okay, yes, sir. I'm seeing that, sir.
All right. So there's no outside of you guessing and possibly getting it right. There's no way for you to determine that other than what we have done here.
Okay, sir, understood.
All right. And just for your benefit, since you asked, we have done questions with 4 units, and in those circumstances, we have found where 2 of the units reach their maximum, which means that we would have applied this particular approach twice in order to determine that the 2 units have reached their maximum, and therefore at the end we just divided the remainder among 2 units at the end. So I'm sure there are other approaches that persons may have encountered, but I prefer to provide you with information so that you err on the side of caution, no?
Yes,
so that's
sir,
my recommendation. All right. Where are we? Okay. All right, so good. All right, so I'm just taking note of those who have submitted. All right, let's go now. So the question is not finished. What the question I asked for was the plant lambda, right? I believe that was it. So you're asked for determine the incremental fuel cost of the plant and the total cost. So what will be the plant lambda? Who is next? Ms. Downer? Ms. Downer?
Hi, sir. Yes, sir, I'm here.
What's the plant lambda?
Sir, would it be lambda 1 plus lambda 2 plus lambda 3?
Why you say that? Tell me where in your notes you say that. All right, I'm being unkind because I know it's not in your notes. So I want you to tell me why you say that.
Sir, sir, could we do it separately for each unit first?
What is the theory we just applied? For economic dispatch, what's the condition?
I'm determining the additional power or seeing
what's the theory that governs economic dispatch? Because all that we have done is based on economic dispatch. If the units are not being dispatched based on ED, yes, then what we have done would be of no consequence. We would then have to look at just the generation technology. So we'll be looking at generation dispatch, which will be based on technology, the availability of crew and all of that, which we went through a couple weeks ago. But here, we are using economic dispatch. So I'm asking, What's the basis for that?
Lambda 1 equals to lambda 2 equals to lambda 3.
Well, what? So lambda 1 equal lambda 2 equal lambda 3 equal?
Lambda.
Lambda, and that lambda represents what?
The plant lambda.
Plant lambda. So at the point I'm supplying 800 megawatts, what is the lambda for the plant?
Sir, 800.
Go again?
$800, sir?
No, man. Plant lambda. So the places, all right. So the places help out Mr. Owner.
Yes, sir.
Help her out. What's plant lambda?
The plant lambda was 38.12.
38.12. I don't know. You are the one.
That's on the slide previously, yeah.
All right. Okay. So that's the plant lambda, which is equal to lambda 1, which is equal to lambda 2. Of course, why wouldn't it be equal to lambda 3?
Because lambda 3 is the previous one from before.
No, give me a better answer. Why wouldn't this be equal to lambda 3?
Because lambda 3 was calculated when the load distribution was different. Lambda, yeah.
Don't overthink it. What does lambda represent? Define it.
It's the cost per megawatt for the plant.
Cost per megawatt hour.
Yeah.
Define it. Define it. You have just told me the units, but I want you to define it.
It's the amount of money. Is the how do I explain this?
You can't use the econ, you know.
It's the cost that the plant, the expenses that the plant goes through to generate 1 megawatt.
One additional. That's the key. The incremental cost is the cost for producing one additional unit of output. In this case, the unit of output that we are looking at is a megawatt. So I come back to the question, why couldn't this not be equal to lambda 3? What does lambda 3 represent?
The incremental cost of
unit 3.
Of unit 3, yeah.
Okay, so I'm asking, you know, why isn't this, or why couldn't this be equal to lambda 3? Because the theory says lambda 1 equal lambda 2 equal lambda 3 equal lambda plant. Why isn't this, or couldn't this be equal to lambda 3? It's a simple question, you know, don't overthink it.
Because lambda 3 has been maxed out.
Oh, unit 3.
Unit 3, sorry, unit 3 has been maxed out, and as such, the incremental cost. I'm trying to think of the best way to put it. The incremental
just
cost.
Tell me, all right. Just assume that you're talking to Michael.
That's a hard assumption, but
Pardon?
Unit 3 has been maxed out, so the incremental cost will not go up.
No, not its incremental. Well, fine, but unit 3 has reached its maximum, and therefore there is no possibility for an additional megawatt to be taken from it.
Yeah.
All right. So therefore, its cost of production has been capped because it has reached its maximum. There's nothing you can get from it. So there's no cost per additional megawatt from unit 3. Are we clear?
Yeah, I get that.
Which is why the plant lambda will now be dictated by units 1 and 2, because those are the units which are producing the additional megawatt to the system. So the theory, the definition has to stand, eh?
Yeah.
Everybody with it?
Yes, sir.
All right. So lastly, what's the cost? How do we find the cost of production?
We substitute the lambda value into the formulas we substitute the lambda value into
Lambda value?
the lambda 1 and lambda 2, the lambda of the plant, into the formulas for unit 1 and unit 2.
Do I help him? Do I help out with places?
Sure. The P1 and P2 that we found at this lambda value, the dollars per megawatt hour, we substitute it in the cost functions that we got before in the question.
And what were the cost functions?
F1 is equal to 0.07.
Okay, so we substitute them into F1, F2, and F3. Excellent. So you put P1 into that, P2 into that, and P3 into that. Because these are the functions. Those are the cost functions. And so at the end, you would get a cost. And what's the unit? What's the unit? What's the unit for the cost function? It's cost function, and what's the unit?
Dollars per megawatt.
Dollar per hour.
Dollars per hour.
Dollar per hour.
And one of the beautiful things about the cost being in dollars per hour is that you, as an engineer, I hope it brings it home that you recognize that in running these plants, you're actually burning money by the hour. Okay? So efficiency is important. You have to think about what you're doing. You have to think about storage, how much it's costing you for storage, because the cost functions, as you see it here, yes, there are some fixed costs. And those fixed costs are things that I just mentioned in terms of personnel, in terms of storage, all of these things. So whether or not you're running the plant, whether running the unit, you still have these dollars per hour. Everybody cool with that now?
Yes, sir.
All right. Any other questions? Because we want to just go into the rest of this generation thing.
Sir, I had a question, sir. Well, I didn't work the question at this point, but I'm not going through a while ago. What if we had when we did lambda 1 and lambda 2, unit 1 and unit 2, what if we had reached the say unit 2 maximum, which was check from the tables. Say about, all right, say take unit 1 for example. Suppose we had reached a 250. We'd actually have to take the same approach, which we subtract the both unit 3 and unit 1 from the total power to go about to find the additional on unit 2.
Yes.
All right.
So if one of the other 2 units had reached its maximum, you take that out, and then it means that the last unit would be the one providing the additional.
All right, sir. Thank you.
You're welcome. All right. So most of what we're gonna just move on to to wrap up this whole power system management thing. We want to talk a little this afternoon about renewable systems integration. Now, much of what is expected to be done in this particular topic will come out in your project. Okay, so you can, for use of a better word, you can use this afternoon's lecture as a guide to some of the things you need to be thinking about when you look at your project. All right. So let us get started. So we're talking about renewable systems integration, and we want to just appreciate it, appreciate what it's all about. Yes. So it's about incorporating these systems. And in some instances, you'll hear it referred to as distributed generation, dispersed generation, embedded generation. So those are some of the terms you'll hear persons refer to for generation that is placed inside an existing network. Now, for the most part, embedded generation or distributed generation is connected at the distribution level of your power system. All right? So when you hear them talk about dispersed generation or embedded or distributed generation, it's usually at the distribution level. However, the large-scale renewable systems are now being connected at the transmission level. So in other words, they're providing input at the same voltage levels as the traditional generating plants. Okay? So the integration that we're talking about is looking at energy storage, you know, how we treat with the interaction with thermal plants, yes? And look at how this will impact the distribution and transmission system. Yes, Mr. Smith?
Good evening, sir. Going back to the question that, good afternoon, sir, and everyone at that. The question that I just asked, sir, about in the scenario of I think he was referring to Unit 2 or
no, Mr. Smith. My apology,
yes,
but I'm going to ask that you just refer back to the recording for that. We have to move on.
All right, sir.
Thank you. Okay, so this is really what renewable system integration is all about. And so we can look at some of the goals that are out there for renewable energy or renewable system integration. Some of the goals, you know, reducing carbon emissions. That's one of the key goals for use of renewable systems. You know, reducing any form of air pollutant. All right, so we are seeking to get rid of or reduce NOx and SOx. NOx being oxides of nitrogen, and then SOx, oxides of sulfur. Yeah. Which would, and you know, a lot of this would have emanated in parts of Europe, for example, where acid rain has had devastating impacts on a lot of their infrastructure. And so in reducing these air pollutants, you are reducing, you know, the acid rain and its deleterious effect on the environment, right? And so you want to seek to get cleaner renewable systems, as renewable energy systems as part of your mix. One of the areas of focus that I'm interested in is really and truly how clean is renewable energy, because we have to do what is referred to as the energy balance to see in terms of the aluminum that is part of the production, in terms of the silicon that is part of the production, in terms of the fiberglass that's part of the production. How much energy, how much fossil fuel energy would have been used in producing these raw materials, you know? So you have to think about from the bulldozers that are used to mine the ore, because they use fuel and they are producing emissions, carbon emissions. So when we do an energy balance, then we can see whether or not this beautiful, pristine looking wind turbine, how much is it really removing in terms of pollution from the environment? But that's for another day, and maybe, you know, another or a good research project for someone who has that sort of interest. Anyway, we want to increase asset use through the integration of distributed systems. Yes. You hear it all the while. Oh, we have so much sun in Jamaica and we have so much wind in Jamaica. Why aren't we using more renewables? Jamaica was, you know, I think even the recent heavy rains, for me, yes, they were devastating, but for me, it is just a reminder of what the Arawaks came and saw, you know. The ex-Jamaica, you know, spoke to the fact that this was a land of real wood and water. And so these flood rains, they have come as a surprise to us, but the reality is, in many instances, we were the ones who have encroached on these waterways because we have always been, or we were described as land of food and water, but we mash up the place and we saw it dry. But during these times, you know, devastating as it is, don't get me wrong, devastating. It's just that the waterways that were in existence, you know, as an example, I saw the Rio Minnow in Spate on Sunday. I have not seen water in that riverbed for about 5 years, you know. And of course, I'm sure someone who has not been familiar with that area may have built close to the bank, you know, thinking that they are fine, but, you know. But anyway, I digress. We have these assets, we can use them. We have the sunshine, we can use them. And so the question is, why not get them as part of our system? Yes?
So good, actually.
Yeah, I submit to you back in the 1990s, the idea was that 15%, 10 to 15% of renewables as part of our national grid was just too much. Yes, but today we have settled on 30%, and the current government is looking at increasing that to 50%. So we have come a far way. Yes, we have the assets, why not use them? In terms of customers, customers must be able to integrate at their level. So, you know, regular householders use up the RE. And if you have excess, be able to sell it back to the utility company. So, you know, we have been changing. We have been making some advances in this area. So the first goal is to reduce emission. The other one is just to use up the assets that are available, the renewable assets that are available. Again, to support our achievement of renewable portfolio standards, yes. In terms of, as an example, and this is a classic example, many of the Eastern European countries, they have a lot of fossil fuel available to them, believe it or not. And to become part of the EU, many of these countries of the Eastern Bloc were forced to attain certain renewable energy targets in order to join the bloc. And so you can, you know, do some background reading. You see that a number of them joined up in 2004, for example, and 2002. And this was after having gone through years of trying to reach the RE targets that were set by the EU. And then we also have to consider, you know, enhancement of reliability, you know, security and resilience from microgrid applications. Why do I mention this? Because in terms of just how the power system has developed, and I think I don't want to make any pronouncements, but I do think that in Schoology, there's a link I have there for oh Lord, it slips me. Maxwell and Tesla. The fight between Tesla and okay. Anyway, where they were looking at three phase versus single Edison versus Tesla. Yes, Edison versus Tesla in terms of three phase versus single phase connection. I mentioned that because in the olden days, what we had were microsystems. So you had small generating systems supplying small locales. And in terms of moving to three phase provided the opportunity because Edison was looking at us using his DC supply, which would only take him to short distances. And once it went beyond a certain distance, then, you know, the voltage drop situations and he'd be out, you know, the systems were rendered useless. But Tesla with his foresight now is looked at three phase systems and the fact that you could now transmit high voltages over long distances. So why I'm mentioning this is because we moved from micro generating facilities that were supplying small locales to where we started to centralize generation. So you know, move to centralized generation. In the case of Jamaica, we now have most of our generation on the southeast coast. So we have generation the bulk of our generation concentrated in Kingston and St. Catherine. We have now moved to have, you know, Bogue expanded, so you now have more generation on the western end. So we have now centralized our generation. And having centralized them, we were looking at pushing power in one direction, which is going from the generating plant to your customer. Where we are today is that individuals, even householders, are generating their own electricity and are now putting it back into the system. So the question is, you know, when we talk about integration, we have to think about security and resilience in terms of microgrids and their applications. Yes. So these are some of the things that you would have to consider in terms of when we have the discussion about renewable integration. And let me make it abundantly clear, I am not teaching renewable energy here. I'm speaking about it from the standpoint of the power system. All right. There's a course, I think Dr. Chambers delivers it on renewable energy. I don't know how many of you may have done it. Anyway. Also, you know, looking at reducing the amount of oil we use, that is part of the challenge that Jamaica has in terms of reduction. I may have mentioned to you before the Integrated Resource Plan, or the IRP. These are some of the considerations that have been made or have been focused on for the IRP in Jamaica up to 2038. So this plan, and I pull this from the IRP just to help you understand in terms of our own energy plans for the island, what are some of the things that we're focusing on. So we're looking at things like reliability of the energy supply chain. In terms of from a renewable energy standpoint, we have, in terms of the raw material, sunshine. And of course, we know that wind is a function of heat. Yes? So we have the sunshine, we have the wind. All right? It means, therefore, that in terms of supply of raw material, if we have more renewable in our system, then, you know, we're not that dependent on what's happening out there. But also, because the IRP not only looks at renewables, part of the reliability chain here speaks to our use of things like LNG. So we are diversifying our supply to ensure that we are not overly dependent on any one fuel type. All right, so reliable energy supply chain, diversity of supply, and note together, those represent 50% of the considerations for the IRP. So you're now looking at, you know, increasing renewable energy. Right? Key component of what we have here. And then we come back down now to item 6, environmental stewardship. So part of the considerations in terms of planning our energy is about the reduction in emissions, right? So that's a key focus of the government of Jamaica. And of course, in the mix is that we want to provide customers with a lower cost of energy. So at the end of the day, whilst the cost of renewable energy systems are coming down, we recognize that, you know, that in of itself will help to bring the overall cost of electricity down. And as a part of the overall consideration, you know, this is given 1/6 of the in terms of preeminence as in the IRP. All right. Any questions so far? Everybody gonna sleep early?
No, sir, still here.
No, sir, we're still here.
Just about. All right, cool. So what I want to do is just look at some of the things that would have to be considered when you're looking at a renewable, when you're looking at the use of renewable energy and integrating that as part of your electrical grid. All right. So we have some considerations. We have what I call the electrical considerations. Yes. So we know, based on what we have been discussing, you know, what we have seen so far, we just did it when we looked at economic dispatch, that the power system consists of several generators, and these are, you know, operating in parallel. And this creates what we refer to as an infinite bus. All right. So an infinite bus, what do we mean by that? An infinite bus is one in which the voltage, and this now in terms of the magnitude and angle, they're the same load angle that we're talking about recently. All right, so V and delta. Okay. So V and delta remains unchanged regardless of changes in load or individual generation facilities. What do I mean by this? So at your infinite bus, the frequency will remain constant. The voltage, and usually when we refer to an infinite bus, we usually give it 1 per unit at angle 0. Okay, so that's the idea, right? And what we're saying is that if I add a generator to the infinite bus, because all the other generators that are behind that bus will be operating at the same frequency, etc. What that means is that the generator that I add to the system must conform to the system conditions. Do we understand that? Is that clear?
Yes, sir.
All right. So if I'm connecting a unit to the bus, that unit must conform to the conditions. So even if the unit, and I'm gonna mention briefly this whole business of synchronizing a generator, but even if the unit that you're adding isn't fully in sync with the network, because it is being added to an infinite bus, the bus will pull it into synchronism. Meaning, when it joins the infinite bus, the frequency of that incoming unit will now conform to the frequency of the bus, of the infinite bus. All right? Because of the existence of all these generators. And so, you know, I just mentioned it. The other thing we need to consider, so we're looking at the electrical considerations, right? First talk about the infinite bus. The next thing we need to talk about is synchronization. You won't be able to supply power from 2 generators unless they are in sync, unless they are in step with each other. And what we mean by being in step, it means that they must be operating at the same voltage, the same frequency, and the same phase rotation or phase sequence. Okay? So you can't have one operating ABC and the other one operating ACB. They won't mesh. Right? So they must have the same phase rotation. And so the integration of renewable systems must take into consideration the fact that the incoming generating facility must be synchronized to the existing network. Otherwise, it will not work. All right, so we need to also talk about how do we ensure synchronization for the various technologies. All right. The methods of synchronization, and I know I am sort of dabbling a bit in what you would have done in machines, all right, machines too, but I'll mention it anyway. So the methods of synchronization, you have your lamp dark, your lamp bright, and of course you can use your synchroscope, all right. So these methods can be used to determine, you know, how you synchronize your generator with an existing system. All right. As I said, these are things that would be done in machines. Okay. Now, whilst these methods, you know, primarily refer to rotating systems, yeah? There are some renewable systems that use rotational energy, yes? Some, of course, you know, in terms of integration, comes from static devices. But these methods for synchronization primarily refer to rotational generation. Okay. So we have talked about the infinite bus. We have talked about the need for synchronization. You know, the systems being in sync with the existing network, because you are imposing new generation onto the network. So that is something that has to be considered. The other consideration for renewable system integration is that you're really not going to be building a system from scratch based on renewable energy systems, yes? So you will always be integrating RE systems into an existing network. Now, I mentioned earlier that your traditional network would operate from a centralized generating facility, and it will be managed through localized switching networks. So in other words, you have breakers in your power system, you know, and breakers are not just used for interrupting based on faults. You know, you also can use it for switching. All right. So if you want to open a circuit, you open the breaker. Right? It doesn't have to be that there's a fault for you to open a breaker. Okay. And so in terms of how the network is set up generally, you're going to have your different protection at different points. Even in the distribution system, even at the distribution level, you still have your fuses. And in some instances at the distribution, you have some what we call self-protected transformers, yes, SPTs, which are transformers which carry a breaker on them. All right. So you have your protection at the transmission level. You have your protection at the distribution level. However, for whatever reason, whether it be a fault, yes. So whether it be a fault or some other activity, whether it could be maintenance, you may need to open your circuits. So you may need to even open some fuses on the at the distribution level. The question is, given that you have now put in your renewable systems, or you have your embedded systems, in many instances, they will continue to supply electricity into the network, all right? Or into that part of the network that they can reach. And this phenomenon, we refer to it as islanding, which is where power is injected into a small portion of the network with loss to the greater part of the network. Are we clear? So there has to be, to avoid harm, which can be to the workers from the utility company, or it could be damage to people's equipment. Bearing in mind, students, that a step-down transformer is also a step-up transformer. Yes? So although, for example, you may be at home and you are generating electricity at 110, you're getting that 220. Yes, you're getting that 220 from a pole-mounted transformer, which is taking the voltage from 24 down to your 220. Yes, but if you then put 220 back on that side of the transformer, you are then putting it back up to 24. So even though, yes, you have the disconnection, and that may be, as I said before, maybe deliberate on the part of the utility company for maintenance purposes. If there isn't also automatic disconnection on the part of the renewable system, right? If there isn't disconnection or isolation on the part of the embedded generation, which will then quickly isolate it from the grid, you may cause damage, yes, or injury to personnel. So that's another consideration when we're talking about renewables and the integration of renewables, right? And so persons who are giving consideration to generating their own electricity and maybe considering selling it to the utility company, these are some of the checks and balances that the utility company will have to make before you are granted the license. So if you want to sell back to the utility, yes, you'll have to get a license from the ministry. And part of that licensing process is that you have to show that you have the ability for quick disconnection should there be loss of power coming from the grid. So you are not there then sending power back into your neighbor's home. Are we clear on that? And the separation time will be dependent on individual utilities, and will also be governed by the various standards, whether it be IEEE, IET, or I should say ANSI IEEE, or IET. Any questions so far? Or we're so finished here. Any questions? Is everything clear?
So far, sir.
Mr. Vinay, so like us, only you and I in the room. Anyway, we
No, I don't think that's so.
No, sir. No, sir.
So Vinay,
Yes, sir.
We'll continue talking. Right?
Yes, sir.
All right. Now, we want to also consider, now we have looked at it from the standpoint of the network, the electrical network, and the considerations that would have to be made. Now we need to switch and look at the operational features. Yes. And in terms of how do these RE systems operate, we have to consider that in determining how they are integrated, how we put them into the grid. Now, RE systems most of them are not dispatchable. So we can't turn them on and off as the need arises. All right. Obviously, I can't turn on a solar plant at 6 p.m. All right. You have to take it as you get it. All right. For those who may be familiar with solar, even for your home, yeah. The past couple of weeks, you know, many persons may be crying about the fact that they have the solar system, but they're not getting much from it. But I suppose we have to balance. For about 9 months, 8 months out of the year, we hardly had any rain and we had brilliant sunshine, you know, so we benefited a lot from the solar. Now we need to give back, I suppose, with all this rain. All right. So we can't turn on and off RE systems as the need arises. We can't turn off the wind. We can shut down the water for the hydro, right? But it is better to allow the hydro just to run and we use it as it comes rather than be shutting it on and off, you know, using floodgates or whatever else. And then, you know, when you know, during a drought, we don't have it. So in terms of the technologies, how they operate, we have to make decisions about them. Yes. The other difficulty is that we can't tell the time taken to lose all our part of the generation. So let's think of solar. I have literally stood and watched solar generating facilities here in Jamaica move from supplying close to maximum, and we're talking about close to 18 megawatts of power, and see that just, I'm standing there looking at it and see it drop to about 2 megawatts in no time. Why? Because you have a beautiful cloud that just comes in the area and covers that solar plant. Now, in other jurisdictions where the plants, you know, possibly maybe as big as, you know, some parishes here in Jamaica, yeah, that may not be so much of an issue because, you know, the cloud do not cover everything so quickly. But the bottom line is you can move from peak generation to nothing depending on the type of RE you're using. So in terms of integration, we have to give consideration to that. If I'm using solar, do I want solar? In terms of the size, and where do I put it? Do I put them close to each other? Do I just put them wherever I have land available? Right. So in terms of how they operate, you know, just the features, the operational features of the RE systems, you have to give consideration to that. And so, as I was just saying, these are some of the things that you want to be looking at. And I'm not giving an exhaustive list here, but these are some of the important ones. Yes. Proximity and the capacity of the facilities. Do I want a solar farm in all right, where do I know? Since I know Manchester. Do I want a facility at Kendall, and then I want one in Christiana, and then I want one down by Content? These places are relatively close. So it means that if one is impacted by cloud cover, the others may very well be impacted similarly. So in terms of proximity to each other, I have to think about that. In terms of capacity, where do I put it on the grid? Yes. Do I want to put it in a place where that is densely populated. Yeah, so I want to put it near to a place that's densely populated. If I do that, I'm going to be running some big risks because, again, coming back to solar, if I lose the solar as quickly as it can be lost in a dense, near to a densely populated area, then it's going to impact those customers. At the same time, if I put a large RE facility, extremely far from where the energy will be consumed, I have to consider the losses. I have to consider the cost of strengthening the grid to get it to where it is going to be used. So these are considerations that will have to be made. And as I said at the beginning of the class, much of what I'm saying today, you need to use it as part of the project that you have to do for this module. Reserve margins. We spoke about reserve margins already. In terms of the facilities I have, the renewable facilities, what sort of margin do I need? I told you in the first lesson on the management that, this 10% rule. But is the 10% rule now out the window, given that we have so much renewables on the system? Can I survive with 10%? Or do I need to go where we are now in Jamaica to 20%? Because with that 20%, when I lose an RE facility because a cloud comes in on the wind. So in one instance, I'm getting the benefit of wind energy because it's nice and windy. But that same wind brings in some nice clouds. And so my solar facility goes. So I have to think about my margins. I have to think about storage. And storage not only deals with things like solar. Do I want to store that energy? And this is where our physics now comes in, because I can store that energy by just pumping some water. That is stored energy. So I now have that potential energy, which I can then transfer to my hydro system. And then finally, we talk about grid support. You just did the lab, yes? In terms of we understand that many of the conclusions were not very clear and the discussions were weak, but the bottom line is we understand, I hope we now understand and can appreciate the importance of VAR support. And it's VARs in terms of injecting VARs into the bus. Depending on the technology that I'm going to be using in terms of the RE, I may need to have VAR support, which is what I'm referring to here as grid support. Okay? So we want to just quickly look at the technologies. We start with wind. And the wind system, yeah, as you can see here, in terms of the production of electrical energy, it's quite similar to your thermal plant. The only difference is that where the turbine is for your thermal plant, that is then replaced by that. Your gears and your hub. Everything back here is like your regular plant. So in that nacelle, which is the housing, what you see at the back of the turbine, that big thing at the back, yes? That contains your generator and your transformer. Yep. Up front, you may have some gears, or depending on the technology, it may be done using static devices, yeah, variable speed drives. Okay. So the rotation is coming from the wind. Yes. So the rotation is being produced by the wind across the blades of the turbine. And nothing fancy about that. But you have the wind in terms of the wind speed can vary. And so you have different technologies that are used. Yes. If you have a fixed speed wind turbine, where it is coupled and you're getting a fixed speed regardless of what is happening out there, then the technology in integrating it, because remember we spoke earlier about the need for synchronization, yes? For it to be synced with the network, then you have to find a way. How do I connect it? We'll talk about that in a few. But you have variable wind speed generators. You have generators that are going to be using, turbines that are wind turbines that are going to be using synchronous machines or induction machines. If it's induction, then where is the VAR support coming from? Because it will require VARs to operate that induction generator. So these are considerations that will have to be made when we're talking about integration. I know I'm giving you a lot of stuff here this afternoon, but you know, this is what now makes modern power systems interesting, because it is not just about, you know, a thermal plant with turbines and all of that. We're now talking about a lot of power electronics. So if you're more leaning towards that type of thing, you still have a place in the power field, because this is where we're going. So we have the gears, as I mentioned, the variable speed drives, because this would now help us to get that output, which would allow us to be synchronized to the system. Of course, I'm oversimplifying a lot of what we have here, because in terms of the wind systems, those are coupled and they are brought to a substation on the facility, and then from that substation into the electrical grid. All right. Yeah. Now, we can't dispatch wind. And I'm saying that almost tongue-in-cheek, because this is one of the areas that I've given a little more focus than others. And whilst we can't dispatch wind, in terms of the ability to forecast, that has been improved over time. And so we are able to give a better understanding or a better guesstimate as to what the output from our wind systems will be, you know, within a particular time. And the other thing I want to mention, and it may come as a, you know, many times you would be driving along and you're not really feeling any wind, but yet you see the turbines, the windmills are spinning. Yeah. Usually the upper level wind is a little heavier than what you'll get at ground level. All right. But the point is, whilst it's intermittent, it will not move suddenly to zero. So in terms of storage, that may not be so critical, because whilst you will get a gradual decline of the wind output, yes, it will allow you, and I say you, I'm talking about as a utility, it will allow you a little time to make the necessary adjustment, right? Where you can now start bringing in generation that can come online, you know, the fast acting generation that we mentioned before. You can now start bringing in those, and it could also be renewables, because it could be hydro, depending on the type of hydro you have. Because hydro, although it is renewable, depending on how it operates, it can be dispatchable. So you can turn it on and off. So the point about wind here is that, unlike solar, you can, you have time to make adjustments, okay? In terms of the interface, as I mentioned before, this will be dependent on the technology used in the turbine. So we do have some old turbines here in Jamaica, such as Wigton 1. Those are induction type generators. Yep. Those came in the early 2000s. So in terms of technology, they are kind of out. The newer ones, I don't want you to quote me on this, but I think many of the newer ones are synchronous machines. So in terms of the VAR support that they are taking from the network, it wouldn't be as great. All right, so to operate the Wheaton ones, they would have had to put in capacitors in their facility in order to operate those turbines. Whereas the others would not require that sort of demand. So to support the different technologies, the options that you'll have would be for like self-starters, use of fixed speed turbines, for your synchronous generators, which will operate at synchronous speed. Synchronous speed, of course, would then dictate what the system frequency would be equal to. Okay, and soft starters use, thyristors, and I suppose by now you realize I am not a fan of power electronics, but I have to do it because I'm in this field. But your thyristors to produce appropriate frequency in terms of the interconnection. I also mentioned that you would need VAR support. All right, so you use VAR support for your induction type generators. I mentioned that. And then lastly, I know we're running out of time, so I know I'm going a little fast now. You're gonna put a wind farm where you have good wind regime. There's no point in putting down a wind farm and then hope and pray that it gets windy. So you'll have all of these tests that would have been conducted to determine where you can put on the wind farm, right? But that's only half the battle. It may be that where you have wind is not necessarily where you will have the appropriate grid connection point. And so it would require significant investment in strengthening the grid at these points in order to get it into the network. All right. So whilst one of the, and I don't know if you heard the reports coming out of the last annual general meeting of Wheaton, where they said we're going into farming. No, this is something that may seem far-fetched, but the reality is wind farms require large footprints. And by that I mean you need large expanse, right, to put on a wind farm. Because you do, and one of the reasons is that, once the wind passes over the blade, you're then talking about the wake of the blade. So just like an aircraft, you'd have a sort of vacuum being formed behind the aircraft. So you have that being formed behind it. So you need to space them. The fact that you're spacing them means that you have a whole heap of land. And so it provides facility for farming. So Wheaton is not far off on that. But at the same time, because you are now in that sort of area, you may not necessarily be close to the point on the grid where the power being supplied from your plant can be effectively or efficiently utilized. All right. All right. And so let me just wrap the other two. For hydro, we know that hydro is formed or produced when, the rotational input, we have water flowing across the blades of a turbine, and this drives a generator. So the technology in of itself is quite similar to what you would have had with the thermal. It's just that the thermal, as we now know, is produced from heat. Yes. So your hydro generation is just the water moving the turbine blades, and then the turbine drives your generator. Right? Nothing fancy about that. And so your turbine, want to go do this? So your turbine, here's your water, right? And the water drives your turbine, and then the turbine is coupled to your generator, and the generator then goes to your network. Okay? Now, based on the considerations I gave earlier in terms of protection, etc., because your hydro plant is usually part of the bigger network, some of the protection considerations would have been dovetailed into all of that. So in terms of having a separate or specific disconnection systems. That may not be necessary because the hydro plant would be part of the bigger network. All right? I hope you understand that. In terms of technologies, you have run of the river. I also have water storage facilities. And I'm talking about here reservoirs, dams. And I just want to make it clear that run of the river may have storage facilities, but these storage facilities are just to ensure that you have continuity of supply. So you're not having a big holding area for water. It's just that you have it so that you're managing the flow. All right. So it's still run of the river, but you're just managing the flow in terms of the water coming in. For the water storage, you have reservoirs and your dams, which means that you can actually dispatch hydro plants. So hydro plants are dispatchable, especially those with storage facilities. Okay. Now, you can have the storage facilities where the water stored is coming from rivers, all right? But the primary operation is that you're using a storage facility. I hope you understand that. And the water from the storage facilities can be returned by pumping. So after it is used to drive the generation, to produce that electricity, we then pump it back into the storage facility. All right. And as I said, I may have said it at the beginning of management, that we have pump storage, okay? And that hydro is one of those generation that can quickly come online. Now, this may not necessarily be for your run of the river, but for your pump storage, for where you're having storage facilities, then you would be able to bring these online to deal with any form of shortfall you have in your network. All right, and yeah. And then finally, we have solar systems. And the two that we can focus on are your concentrated solar plant, your CSPs, or your photovoltaic. Mainly in Jamaica, in Jamaica we use photovoltaic. But in places like California and some of these areas, you may find CSPs, which is basically for your CSPs, they operate just like your thermal systems. So you're using the sun to boil water. So the sun now provides the heat towards the generation of electricity. Okay? And then for your photovoltaic, at the heart of it is your inverter. And that inverter provides the interconnection with your power system or your grid. Yes? And one of the benefits of this is that because it's static interconnection, you can use it both with your 50 or 60 hertz. So if I buy an inverter in the US, I can use it in Jamaica at 50. I just have to go in and make the necessary settings in that inverter. And then, if I decide to move to Cuba or move to Antigua or St. Kitts, I can take it with me and go use it there and their 60 hertz systems. Yes? So it allows you to use different frequencies because of the type of interface. And then the last thing for today, you require, if you're going to be interfacing in selling power to the grid, you require to have special protection to avoid islanding. And storage is a critical component of solar systems. In the past, Jamaica, we allowed solar systems to come in, or to be installed that did not have storage, but that has been, that is now a thing of the past, all right? Where persons now, or institutions who are interested in supplying solar to our grid will be required to put up storage facilities. All right, so I know this has been a mouthful, but it will, as I said, help you or provide some direction, I hope, for your project. It is now 5 o'clock. I thank you for your patience. I know I rushed a bit at the end, but I trust it was worth it. So when next we meet, we look at substation fundamentals and talk about some some stuff regarding substations. All right. Okay, that's it from me for today. Any questions, any comments, and then we can move on. All right, that's it.
Sir, I have a question. Good evening.
Yes, Ms. Michael, go ahead. You're low. Raise your voice a bit.
Hearing?
Go ahead.
For the CSP, the solar one, you said that it's used to boil the water, so it would then be classified as a steam turbine or a
Yes.
steam generator. Okay.
Yes. So in terms of a thermal system, your regular thermal system where you'll be boiling water to produce steam, etc. Yes?
Yes, sir.
The CSP is used for that.
Oh, okay, sir.
And one of the beautiful things about it is that it can provide its own storage in terms of it heating things like brine or salt. So you'll have that heat energy maintained in those facilities. So you can still get the benefit of the CSP without sunlight.
Oh, okay, sir. So, and you would need a wide land space or a wide area.
Huge facilities.
Okay, sir.
All right, thank you. Have a good afternoon and rest of the
question.
Evening. Yeah, go ahead.
As it relates for the orals tomorrow, sir, do we need to have the power systems or power program on screen, sir?
Oh yes, thanks for that. Yes, you will need to have whatever facility you use to conduct the labs. You will need to be able, you will be allowed to, or you'll be required to share your screen. All right, so from, depending on what I'm doing at the time, you'll share your screen and persons will join the class at the time I give in the schedule. All right, so you don't need to wait on me, you just join at that time because I'll be ready for you at that time. But thanks for that question. You need your computer and be ready to share a screen.
All right, sir. Thanks, man.
All right. Take care.